So, all right, moving on to objective 3. We want to use the sum and difference formulas involving inverse trigonometric functions. So for example 4, we want to find the exact value of sine of cosine inverse 1/2 plus sine inverse of 3/5. So we definitely see that there is a sum going on, but it's going to be a little bit on the confusing side. So let's begin by breaking this down a little bit. We know that this is going to look something like sine of alpha plus beta. So first thing we want to do is we're going to let alpha equal cosine inverse of 1/2. We're going to let beta be sine inverse of 3/5. This is now going to give us sine of alpha plus beta. So now we have the sine of alpha plus beta, but we want to actually kind of find what our alpha and betas are going to be. So we have to solve for alpha and beta. So moving forward here, we want to start with cosine of inverse 1/2. So for alpha equals cosine inverse of 1/2, this is going to be on the interval Let's first rewrite it and then we'll define our interval. So for alpha equals cosine inverse of 1/2, we can take cosine of each side. This is going to cancel out our cosine inverse. Then we get cosine of alpha is equal to 1/2, which is now on the interval alpha greater than or equal to 0 and less than or equal to pi. All right, so now we have a specific equation. Now we want to use the fact that cosine of alpha is going to be equal to x over r, where r is our radius. So we use the fact that cosine of alpha is going to be equal to x over r in order to find sine of beta in this case. So if we know cosine of alpha is equal to x over r, we get that x is equal to 1 and r is equal to 2. Now we want to use the equation of our unit circle, or just the equation of a circle, to get x squared plus y squared is equal to r squared, where we see x is 1 squared, y squared is equal to 2 squared, which, simplifying further, is going to be 1 plus y squared is equal to 4. Then if we subtract 1 from both sides, we get y squared is equal to 3, which then gives us that y is equal to the square root of 3. I apologize, I realized I caught something. So we wanted to use this to help find sine of alpha, because that's what we're going to be missing here. That's help, not health. So we want to find sine of alpha because sine of alpha plus beta is going to simplify down to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. So our missing values in this case are going to be sine of alpha and cosine of beta. We already have cosine of alpha and we already have sine of beta. Those values are given to us by 1/2 and 3/5. Since we had that cosine of alpha was equal to 1/2, and then we're going to get that sine of beta is 3/5. So we need to find the missing values, which were sine of alpha and cosine of beta. So, all right. Finding sine of alpha, we found our value for y, which means that sine of alpha, which is equal to y divided by r, is going to end up, sorry, my screen wigged out here for a second. All right, so it's going to end up being the square root of 3 over 2. So our value of sine of alpha is I wrote r over 2, so it's the square root of 3 over 2. We'll highlight this in blue. It's not our final answer, but it's one of our answers. So all right, we found sine of alpha. Now we need to find cosine of beta. So doing the same thing again here. We're going to say for beta equals sine inverse of 3/5, we're going to get that sine of beta is equal to 3/5. We just took the sine of both sides, and this is going to be on the interval negative pi over 2 less than or equal to beta, which is less than or equal to positive pi over 2. And now we're going to use the fact that sine of beta is equal to y divided by r to help us find cosine of beta. So if we're using this fact, this means that y is equal to 3 and r is equal to 5. So we're going to use the equation of a circle to state that we already know x squared plus y squared is equal to r squared. So this is going to give us x squared plus 3 squared is equal to 5 squared, which, simplifying this, gives us x squared plus 9 is equal to 25. We subtract 9 from both sides. This tells us that x squared is equal to 16. We take the square root of each side, and this gives us that x is going to be equal to 4. So if x is equal to 4, then we get cosine of beta, which we know is x over r, is going to be equal to 4 over 5. So this is another one of our values here. So all right, we found all of our missing values, which was just sine of alpha and cosine of beta. We have cosine of alpha and we have cosine of beta, which means that we can now solve for sine of alpha plus beta. And we'll see if we have enough room for it. So if we had sine of cosine inverse of 1/2 plus sine inverse of 3/5, which we said simplifies to sine of alpha plus beta. This is now equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. And now we can plug in our values. So we said sine of alpha was a square root of 3 over 2. Then, we'll actually just multiply, cosine of beta was 4/5. And now the values that we were given, cosine of alpha is 1/2, and sine of beta was 3/5. And now we just want to multiply these values together to simplify. So 4 times the square root of 3 is going to give us 4 square root of 3 divided by 2 times 5, which is 10. Then 1 times 3 is 3 divided by 2 times 5, which is 10. And this gives us our final answer. We're just combining our numerators in this case. 4 square root 3 plus 3, all divided by 10. And that would be our final answer for sine of cosine inverse of 1/2 plus sine inverse of 3/5. 4 square root 3 plus 3, all divided by 10. So a bit of a longer problem in this case. What we really just did was we had to find those missing values. And the missing values in this case were sine of alpha and cosine of beta. So we had to use cosine of alpha and sine of beta to find those other values. And then once we found those other values, we were able to just plug them in order to find the value of our function. So all right, well, let's just review a quick summary of our sum and difference formulas. So we have our cosine formulas, our sine formulas, and our tangent formulas, where those cosine of alpha plus beta was cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Cosine of alpha minus beta was cosine of alpha times cosine of beta plus sine of alpha times sine of beta. Sine of alpha plus beta was sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Sine of alpha minus beta was sine of alpha times cosine of beta minus cosine of alpha times sine of beta. Then tangent of alpha plus beta was equal to tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent of beta. And lastly, we have tangent of alpha minus beta, which gives us tangent of alpha minus tangent beta divided by 1 plus tangent of alpha times tangent beta. That was quite the mouthful. But there we go. There's our summary there of our sum and difference formulas. So moving on, objective 4, we want to solve our trigonometric equations, linear in sine and cosine. So sometimes it's necessary to square each side of an equation to obtain expressions that allow the use of identities. This may introduce extra solutions, which we will then need to check. So sometimes we may end up with extra solutions, but we have to check to make sure that they are actually extra solutions and that they're actually contained in the solution set, not just extra baggage from squaring each side. So all right, let's do example 5. We have solve sine of theta plus cosine of theta is equal to 1, where theta is between 0 and 2 pi. Now, it's going to be really helpful if we can use sine squared of theta plus cosine squared of theta, because we know that that's equal to 1. So we want to be able to use that. So that tells us that we're going to probably need to square each side. But let's just go ahead and identify first that it's better to square both sides. So if we use available identities, so if we use available identities, mostly attributing to sine of theta or cosine of theta, they do not lead, sorry, this is supposed to say using available identities. They will not lead to equations that are easy to solve. So if we just try to replace sine of theta or cosine of theta with something else, it's going to be really not easy to end up solving. So this is why we want to square both sides. All right, so if we square both sides, this means that we're taking sine of theta plus cosine of theta. We're squaring, and we're setting this equal to 1 squared. Remember, you have to square both sides if you want to square one side. So when we square sine of theta plus cosine of theta, we're going to be stuck with those middle terms, but we can deal with those a little later. This will end up giving us sine squared of theta plus 2 times sine of theta cosine theta plus cosine squared of theta, and this is all equal to 1. Then we just want to rewrite our equation a little bit. We're going to put in parentheses our sine squared theta plus cosine squared theta. And then on the outside now we have 2 sine of theta times cosine of theta, which is equal to 1. And now since we have this value, we know this is equal to 1, and we can replace it with 1. So this gives us 1 plus 2 sine of theta times cosine of theta is equal to 1. Where now if we subtract 1 from both sides, this will just give us 2 sine of theta times cosine of theta is equal to 0. Where now we can divide by 2 to get rid of that 2 coefficient, which just leaves us with sine of theta times cosine of theta is equal to 0. So now we need to find solutions for this equation. Separating this out, we know that this just means that sine of theta is equal to 0 or cosine of theta is equal to 0, which in this case, the values of sine of theta that would make it equal to 0 would end up being 0 and pi. And the values of theta that would make cosine theta equal to 0 would be pi over 2 and 3 pi over 2. So these are going to be the solutions that we need to check. These are the current solutions, but we have to check and make sure they're actually solutions. So we'll highlight these in blue, but just know they're not our final answer. So now we need to check all values of theta, which we said are 0, pi over 2, pi, and 3 pi over 2, to see which are solutions of our original equation. And we're going to underline original. This means that we are using sine of theta plus cosine of theta is equal to 1. This is the equation that we're using. Each one of our values of theta are between 0 and 2 pi, so we know that they're all valid. So starting with theta equal to 0, if we have sine of 0 plus cosine of 0, this ends up being 0 plus 1, which is equal to 1. So this means that this is a solution. Theta equals 0 is a solution, so let's highlight that in yellow. Then our next value, theta, is equal to pi over 2. So we get sine of pi over 2 plus cosine of pi over 2 is going to be equal to 1 plus 0, which is 1. So this means that theta equals pi over 2 is also a solution. Now our next value is pi. So we have sine of pi plus cosine of pi. Sine of pi would be 0. Cosine of pi is going to be -1. So this gives us a value of -1, which means that this is not a solution. Theta equals pi is not a solution of our original equation. Then lastly, we want to try out 3 pi over 2. Sine of 3 pi over 2 plus cosine of 3 pi over 2 is going to end up giving us a value of -1 plus 0. So we also get a value of -1, which is again not a solution. So this ends up giving us the fact that theta equaling to 0 and pi over 2 are the solutions to our original equation. If you want to write out the solution set, this would mean that the solution set is curly braces 0 pi over 2. This may also come up in MyMathLab. It may ask which solutions are extraneous. So the extraneous solutions are just the values that we found that aren't actually solutions of the original equation. So our extraneous solutions in this case would be pi and 3 pi over 2, which just means they're not actually solutions. It just means that they're solutions of our equation if it was actually squared. So that's what that means if in MyMathLab it were to ask you which ones were the extraneous solutions. So all right, that one was a bit of a longer problem there. But all we really did was square both sides. We were able to use an identity that we're familiar with and we like using, and then we just had to find and check the solutions from there. So all right, that wraps up our section 7.5. So I'll see you all again in section 7.6.